Hi students, welcome back again to this course, An Introduction to Mechanical Engineering. I am Professor Yao. Laminar and turbulent fluid flow. The keywords: to fasten your seat belt, severe weather patterns, a kitchen faucet, start to oscillate, break up, and become turbulent. Laminar. On the surface trailing edge, the irregular flow pattern to be turbulent, small eddy and whirlpools. Laminar and turbulent fluid flows. If you've ever traveled on an airplane, you might recall the pilot instructing you to fasten your seatbelt because of the turbulence associated with severe weather pattern or airflow over mountain ranges. Try opening the valve on a kitchen faucet without an aerator, or a garden hose without a nozzle, by just a small amount, and watch how water streams out of it in an ordinary fashion. As you gradually open the valve further, you will eventually reach a point where the smooth stream of water starts to oscillate, break up, and become turbulent. In general, slowly flowing fluids appear laminar and smooth. But at a high enough speed, the flow pattern becomes turbulent and random looking. Laminar. When fluid flows smoothly around an object, as in the sketch of airflow around the sphere, the fluid is said to move in a laminar manner. Laminar flow is associated with situations where the fluid is moving relatively slowly. As fluid moves faster past the sphere, the flow's pattern begins to break up and become random, particularly on the sphere's trailing edge. The irregular flow pattern is said to be turbulent. Small eddies and whirlpools develop behind the sphere, and the fluid downstream of the sphere has been severely disrupted by its presence. Reynolds number. The keywords: the criterion, moves in a laminar or turbulent pattern, the size of the object, the speed of the object, the density and viscosity properties of the fluid. Conducted experiments. The transition between laminar and turbulent flow through pipe. A dimensionless parameter. Reynolds number in terms of the ventilation systems in a building, in proportional to. Reynolds numbers, the criterion to determine whether a fluid moves in a laminar or turbulent pattern, depends on several factors: the size of the object moving through the fluid, or the size of the pipe or duct in which the fluid is flowing, the speed of the object or the fluid, and the density of viscosity properties of the fluid. The exact relationship between those variables was discovered in the later half of the 19th century by a British engineer named Osborne Reynolds, who conducted experiments on the transition between laminar and turbulent flow through pipes. A dimensionless parameter, which is now recognized as being the most important variable in fluids engineering, was found to describe that transition. Reynolds numbers. The Reynolds numbers IE is defined by the equation IE equal mu nu L sub mu in terms of the fluid density and the viscosity, its speed, and the characteristic length that is representative of the problem at hand. Characteristic length. For the crude oil that is being pumped through a pipe, the characteristic length L is the pipe's diameter. The water flowing past the surface, L is the surface diameter. For the ventilation systems in a building, L is the diameter of the air duct, and so forth. The Reynolds numbers have the physical interpretation of being the ratio between the inertial and the viscous force acting within a fluid. The former is proportional to density, and the latter is proportional to viscosity. When the fluid moves quickly, it's not very viscous, or it's very dense. The Reynolds number will be large, and vice versa. Homework. Handwriting all keywords and submitting them to Coach Facebook. Just do the online quiz, and see you next time.